In today's video, we're going to look at the force of friction. If you recall, we've started to try and develop quantitative models of how we can actually calculate the magnitudes of certain forces. Last video, we looked at gravity. This video, we're going to look at friction. And there are three types: static friction, kinetic friction, and rolling friction. If you're looking at an object in contact with a surface, that surface can exert a force of friction, and that friction can either be one of these three types. Is how we're going to think about it. Static friction is the force of friction when the surfaces are not moving relative to each other. They're static. They're not sliding or rolling. Kinetic is when the two surfaces are sliding on each other, and rolling friction is when you have some object that can roll and it's rolling on a surface. So how can we model these? Well, uh, the first thing we have to think about is what is the cause? And we're going to start looking at static friction. And essentially, when you have something in contact with a surface, the surfaces are generally not perfectly smooth, so there's going to be some contact points that are very strong, some further away. But if we were to zoom in and look at at a molecular level of what those two surfaces are made of, even though there's not necessarily chemical reaction between the surfaces that are causing bonds, there's still an attractive sort of bond that forms between those two surfaces and causes those surfaces to want to sort of stick together. And that's essentially what's causing this force of friction. The surfaces want to stick together and stay still. So with static friction, that's the force when the two surfaces that are interacting with this force are stationary with each other. They're not sliding in any way. Like, for example, if you put your foot on the ground and run, your foot doesn't slide. They're in contact. Your foot's not moving relative to that surface. You have static friction. Those bonds are keeping that shoe from sliding on the floor, right? So how can we sort of put a number to that? How strong is that force going to be? Well, we'll think about an object that's standing still on a surface. So let's say we have this large box here that's on the surface of the floor. We can identify all the forces on it, right? So it's touching the surface of the ground. So there's going to be a normal force and a force due to friction that we have to consider. It's being pushed by this person over here. So there's also going to be a force due to the push. And we're on Earth, so there's the long range force of gravity. But we've identified all those forces. If we draw a free body diagram for that, we know the normal force is always going to be perpendicular to the surface. In this case, straight up. Gravity is always going to be straight down. The force of the push, this person's pushing it to the right, so it's going to be the right. And static friction is going to be the other force. Now, one thing we know from all forces of friction is the force of friction is always parallel to the surface that's applying that force. So in this case, the floor is what's applying the force. So we know the force is going to be left or right. It's going to be somewhere in the direction parallel to the surface. Uh, and since we know that this is static friction, this box isn't moving, this force of static friction must sort of counteract that force of the push. So it's going to be parallel to the surface and in the opposite direction of the push. And the reason we know it's in the opposite direction is because it's static friction, it can't move relative to the floor, so that it's in equilibrium. That net force is going to be equal to zero in that case. Um, so we can just look at Newton's second law, F net equals ma, and we know in the x direction. So in this x direction, we have the force of the push minus the force due to static friction is going to be equal to mass times acceleration. But since that acceleration in this case is zero, that's equal to zero. We know that the magnitudes of the push and static friction have to be equal. So essentially what you think about is this force of static friction between the surface and the box has a magnitude of sort of whatever it needs to be to keep that object from sliding, to keep those surfaces static with each other. So the way we sort out what that is we look at Newton's second law, F net equal to ma, And since since we can analyze all the other forces, the force of static friction, the magnitude, is whatever it sort of has to be to keep Newton's second law um, true, in a sense. And if you think about it, this makes sense. If we were to have, let's say, let's say we have a different situation where we just have, I'll draw a flat surface again, and you have, I got a coffee cup right next to me. I have some coffee cup sitting on my surface of the table here. I'm not touching it, I'm not putting it. So I want to know what's the force of static friction on that coffee cup. It's not sliding anywhere. I know it's static. Well, I can circle it. I can identify all the forces. It's touching the surface. So there's going to be a normal and a friction force I have to be concerned with. Nothing else is touching it. So I can think of the long range force due to gravity. I have my three forces. I can now draw my free body diagram. I know the normal force is always perpendicular to that surface. I know the force of gravity is always going to be straight down towards the center of the Earth. And there's one more force left, the force of static friction that keeps this object stationary on that surface. And I know it's going to be in the plane parallel to that surface. But its magnitude is whatever it needs to be to keep this object stationary. So in this case, if there were any static friction, this object would start to accelerate left or right. That doesn't make sense. So in this case, the force of static friction would be zero, right? There's no static friction keeping that object stationary because there's no force that's trying to move that object. So the static friction is going to be zero in this case. But again, the whole thing of determining what that magnitude is comes from solving F net equals ma, Newton's second law, and looking at solving what static friction needs to be to make this equation sort of true and still hold. Because generally, you'll know something about the acceleration from the fact that it's static friction and not sliding on that surface. So hopefully that kind of makes sense. It'll become clearer as in our synchronous sessions when we go through examples and problems and start to solve it. But generally, the way I like to think about static friction is its force is whatever it needs to be to make Newton's second law hold still for the way that object's moving. Of course, this situation only holds for so far, right? If we go back to this woman pushing the block here, think of if you've ever moved a heavy piece of furniture. You start to push it, it doesn't move. Again, you push harder and harder, it doesn't move. Eventually, you push hard enough, and that object will start to accelerate. You'll push hard enough that you'll sort of overcome that static friction and get that object to slide. What that means is eventually, uh, if I were to have a small push, that force of static friction would counteract that. As the push gets larger and larger, the static friction grows, keeping that object stationary. Eventually, if this push gets bigger, it becomes larger than the static friction. The static friction can't grow anymore. There is a maximum possible size of the magnitude of the static friction, this Fs max, right? So eventually, static friction will be overcome and the object will start to slide. The question is, how can we model that? How can we determine what the maximum possible static friction is? And the answer is right here. We model it this way. I'll put the answer before I explain why that makes sense. The maximum possible static friction is the coefficient of static friction mu sub s times the magnitude of the normal force. And why does this make sense? Well, if you think about trying to slide something, whether it's on a wall, on the ground, if you try to slide something on any surface, really, there's two things that sort of make that hard to slide. The first one is how sort of sticky those two surfaces are, right? If I'm sliding a piece of plastic on a clean sheet of ice, that's not very slippery. It's going to be very easy for me to slide it, and static friction isn't going to be able to hold it still for to resist much force. So that's what the coefficient of static friction is. Mu s is the coefficient of static friction, and it's a dimensionless number. typically between 0 and 1. And it's, you know, so for something that's very slippery, it'd be something like 0.01, a very small number that makes that static friction maximal value really small. If it's, say two pieces of rubber you're trying to slide together, that coefficient of static friction is going to be much larger than stick them together. And actually, in the textbook, there is a table of static coefficients of static frictions you can use. If this is wood on concrete or rubber on concrete or wood on wood, it'll give you the coefficient of static friction for those two materials. The other thing that can make something harder to slide is the normal force. Essentially, how hard are those surfaces pushed together, right? So if you remember, the normal force is that force perpendicular to the surface. So if we have that situation where I just have an object on a surface again, there's going to be some normal force up. That's essentially how hard these surfaces are pushed together. If they're pushed really hard together, it's going to be hard to slide those two surfaces. If you think back to what's causing friction, you're essentially putting those two surfaces in larger contact. There's going to be more molecular bonds in that. They're going to stick together tighter. So bring this all together, this is how we can calculate the value for Fs max, the maximum possible static friction. Is that coefficient of static friction, essentially telling us how sticky those surfaces are, and the normal force, how hard they're pushed together. So putting it all together, if we want to figure out what the force of static friction is, it can be tricky. We know it's got to be less than or equal to Fs max, right? There's a limit to how hard static friction can push on an object, or how much it can sort of keep that object from sliding. But if there's nothing trying to get it moving, it can also be 0. So that force has to be somewhere between, the magnitude of it has to be somewhere between 0 and Fs max. And the way we generally determine that is by looking at Newton's second law, F net equals ma. And the static friction, the magnitude of it is whatever is going to keep this consistent. We're going to know something about the acceleration, because it's static. We know it's not sliding on that surface. And we know we can analyze and look at what forces are involved in it. That's going to give us enough information to put a number with what our static friction is. Again, this will hopefully get more and more clear, and some of the subtleties associated with it we can sort out and get comfortable with in our synchronous sessions when we go through more examples in that. So that was static friction. What about kinetic friction? Well, kinetic friction is when the object's already started to slide. So let's say, we'll look at the same situation here where we have the woman pushing the block, but rather than that block not sliding and staying stationary when it would be static friction, it's actually sliding. And we're looking at the situation of kinetic friction. Turns out kinetic friction is kind of much simpler in a sense to analyze, all right? Because if this is sliding and this object is moving this direction relative to the ground, so it's sliding that way, kinetic friction rather is the force that's going to try and stop that sliding. It's going to try and bring it to a rest and bring it back to a static situation. So we know that force is always going to sort of be in the opposite direction of the motion relative to that surface, right? So if this is how the direction of the speed relative to the surface it's sliding on, we know the kinetic friction is going to be in the opposite direction. And another nice thing about kinetic friction is it's always going to be the same value, right? Whether you're sliding fast or slow, as long as you're sliding, we model that typically the same way, and it's this. Again, think about the magnitude of friction and what can cause friction to be high. What can cause two surfaces to stick? One is how sticky the surfaces involved are. That's given by our coefficient of kinetic friction in this case. And the other is how hard those surfaces are pushed together, which is this normal force here. So this looks very similar to the maximum possible static friction. If you recall from a few slides ago, Fs max was equal to mu s times n. The only difference here is what the coefficients are, right? In this case, the coefficient of static friction is for when the is different from the coefficient of kinetic friction. When objects are sliding, they have a different coefficient of friction than when they're stationary with each other. And again, if you've ever tried to move a heavy object or slide it across a floor, this kind of might make intuitive sense to you. You push really hard to overcome this Fs max because that coefficient of friction is typically larger than the kinetic friction. But once that object gets moving, it gets easier to push because you're now in kinetic friction, and this coefficient of kinetic friction is smaller than the coefficient of static friction is. But again, this kinetic friction is sort of a much more straightforward thing to analyze, right? We always know, we know for all frictions, the force is going to be parallel to the surface that's applying it. And we know for kinetic friction, the direction is always going to be opposite the direction that the object is sliding on that surface. It's going to be in the direction that's trying to stop that sliding. And another thing for kinetic friction, it's always equal to this magnitude. So in this case, where we have the woman pushing the block, again, we have a normal force up, gravity force down, the force they are pushing with. And since it's moving and sliding to the right, the kinetic friction is always going to be in the opposite direction of the way it's sliding. And its magnitude is the coefficient of kinetic friction times the normal force. All right, the last type of friction that we're going to model or use in this course is what's called rolling friction that has to do with rolling motion. This is extremely similar to kinetic friction, right? But there's a slight difference. If you think back to what's causing friction, so we have the rough surface on the bottom and we have the rough surface of the object that's rolling. If you think about what's happening with rolling friction, this tire's going up that way, the surface here is never actually sliding on the surface, right? The tire is not sliding, it's rolling. So we have these molecular bonds sort of that we've talked about between these two surfaces, right? And with static friction, we're breaking those bonds when we try to push them. We're trying to take this, if that's the one object and this is the ground, we're trying to slide this that way to break the bonds that are forming here, right? And that's one way to break it. But with rolling friction, we're not sliding. What we're doing is we're lifting up this part of the tire, right? This tire is going to roll that way, and it's going to lift off the surface, not try to slide that surface. So we're breaking these sort of bonds between the surface by pulling them up. And that, we're the same sort of interaction that's causing it, but the way that object's moving relative to the surface, this rolling motion, means that the force is going to have a different strength. The thing you're going to have to do to sort of overcome that sticking is going to require a different magnitude. And the way we calculate that turns out is almost exactly the same way we calculate kinetic friction, right? The friction force is again going to be parallel to the surface that's applying that force, and it's going to be in the opposite direction the object's rolling. So if this tire is rolling that way, that's the direction its velocity is relative to the surface. Just like with kinetic friction, the static friction, or the rolling friction rather, is going to be in the direction that's going to try and stop that object from rolling. In terms of magnitude, it's very similar to the way we've calculated our other frictions, right? It has its own coefficient of rolling friction, again, typically much smaller than both the coefficient of kinetic friction and the coefficient of static friction, but basically a property of the materials, the two surfaces, and how sticky they are. The normal force is how hard those surfaces are pushed together. And this will give us the magnitude of rolling friction, and knowing the direction that object's rolling will give us the direction of that rolling friction. And that's pretty much it. You treat it the exact same way you would treat kinetic friction. You can determine the magnitude knowing what materials the two object, the surface and the object you're looking at are, and the normal force. Um, and those are the three types of friction: kinetic, static, and rolling friction. Typically, static friction is the trickier one because it can have that whole range of values between 0 and the maximum possible value of static friction, and the direction depends on the other forces and things involved in the problem. Whereas for rolling and kinetic friction, the direction of that force is always going to be opposite the direction the object's moving relative to the surface. Hopefully, in our synchronous sessions and with the homeworks and that, and when we start working through examples of these problems, uh, it'll become more clear and we'll get more and more comfortable with it. If you have questions on this, please email me, reach out to me, or bring them up in our synchronous sessions, and hopefully we'll get really comfortable with this stuff.